Our topic for today is we have here finite dimensional vector spaces. So before we discuss this, so always recall that in our previous lesson, recall that the letter F denotes a real number or complex number. Also recall that we use also V, and V represents as a vector space over F. So first is we have here span and linear independence. So let's define first linear combination. So a linear combination is a list of vector in V, while in V is a vector of the term A1, B1 plus to AM, BM, where A's is an element of F. So the set of all linear combination of vectors is called span or span of vectors, denoted by that symbol span of vectors. Implies that span vector is equal to A1 V1 plus till AM VM such that A's are element of F. Example, suppose vector is equal to F cubed. So the vector 7, 2, 9 is a linear combination of 2, 1, 3, and 1, 0, 1. That is because 7, 2, 9 is equal to 2 times the quantity of the vector 2, 1, 3 plus 3 and the quantity of the vector 1, 0, 1. So thus, 7 to 9 is an element of the span 2, 1, 3, 1, 0, 1. A vector space that is not finite dimensional is called infinite dimensional. Suppose V1 to Vm is an element of V, and V is an element of span V1 to Vm. So by the definition of span, there exists A1 to AM, which is element of F, such that V is equal to a linear combination A1 V1 plus until AM VM. So consider the equation of whether the choice of A's in the equation above is unique. So the choice of A's. So suppose A1 AM is another set of scalar such that V is equal to a linear combination of A1 to V1 until AM to VM. So subtracting the last two equations, so we'll subtract this and that. So we will have A1 minus A1 V1 plus until AM minus AM VM, which is equal, of course, to, again, to 0. So a list of V1 VM of vectors in V is called linearly independent if the only choice of A's element of F that makes the linear combination A1 V1 equal to 0 is A1 until AM are just equal to 0. So example, we have here a vector in F4 and linearly independent in F4. So if you observe, these three kind of vector is linearly independent to each other. Okay. Now, another example, fix a non-negative integer m. Then 1, z until zm is linearly independent in P of f. So to verify this, suppose that a sub 0 until a sub m is an element of f are such a sub 0 plus a sub 1 z until a sub m zm is equal to 0 for every z, which is also an element of f. If at least one of the coefficients of a's were non-zero, then the given equation, this one, could be satisfied by at most m distinct values of z, which is contradiction. That shows that all coefficient in the given equation is equal to 0. So, tandaan po yun. Kailan po natin matatawag na linearly independent ang isang equation? Kailan rin po natin matatawag na linearly dependent? Yan po, doon po tayo papunta sa ganung punto. So hence, 1, z until zm is linearly independent. Yan po. Kapag naging 0 po, lahat sila, matatawag natin po yung linearly independent. So a list of vector v is called this time linearly dependent if it is not linearly independent. In other words, a list of vectors in V is linearly dependent if there exists A, which is an element of F, not all 0, such that the linear combination plus all the linear combination, the sum of all linear combination is equal to 0. For example, 2, 3, 1. And we have 1, negative 1, 2. And we have 7, 3, 8 is linearly dependent in F3 because 2 times 3, 2 times 2, 3 times 1 plus 3 times 1 times negative 1 times 2 plus negative 1 times 7 times 3 times 8 is equal to 0, 0, 0. Okay. So we have here a lemma. So 2.4 linear dependence lemma. So if vectors v1 to vm is linearly dependent in V, and v1 is equal to 0, then there exists j, which is an element of E2 until m such that the following holds. This is a very important kind of lemma, and this will be utilized all throughout this topic. First, V sub j is an element of span of V. Second, if bj term is removed from v1 to vm or the vector, the span of the remaining list is equal to span of vectors. Okay. So proof. First, we have supposed the vectors is linearly dependent in V, and V1 is equal to 0. Then there exists A's, which is an element of F, not all 0, such that A or the linear combination of the sum of A's is equal to 0. Not all A sub 2, A sub 3 until A sub m can be 0. The one that is only provided is B sub 1, which is 0. But B sub 2, hindi lahat po yon ay 0. Because V sub 1 cannot be equal to 0 also. Let J be the largest element of 2 until m, such that A sub j is equal to 0. Therefore, Bj is equal to negative A over j Bj minus until A sub j minus 1 over A sub j times Vj minus 1. So that proves the letter A. So the letter A tells us that Vj is an element of a span of vectors. So same also here. This is an element of the span of a vector. Now, we go to prove B. Suppose that U is an element of a span of a vector. Then there exists C1 to Cm, which is an element of F, such that U is a linear combination of C and vectors. It's the sum of the linear combination of C and the vectors. We can replace Vj with the right side of the given above. So, yung ginamit nating Vj, that is what we call our 2.5, which shows that U is in the span of the list obtained by removing the J term from V1 to VA to Vm, or the vectors. Thus, B also holds, or the second part of the lemma, which tells that if the J term is removed from the vector, the span of the remaining list is equal to the span of the vector. Okay. Now we have another theorem. So we have theorem. In a finite dimensional vector space, the length of every linearly independent list of vector is less than or equal to the length of spanning list of vectors. So to prove that, again, in a finite dimensional vector space, the length of every linearly independent list of vector is less than or equal to the length of every spanning list of vector. So proof. Suppose that U1 and UM is a linearly independent in B, and W and the W's spans B. So we need to prove that M is less than or equal to N. So we do so through the multi-step process, and note that in each step, we add one of the U's and remove one of the W's. So this will be our step 1. Step 1, the list of W's spans V. That thus adjoining any vector to it produces a linear dependent list. In particular, the list of U1, U1, W1 to Wn is linearly dependent, of course, because it is already a mixture of U and W. Thus, by linear dependence lemma, using as we call that as 2.4, we can remove one of the W's that the list of B of length n consisting of U1 and the remaining W spans V. So, since tinanggal mo yung W's, parang nire-replace mo lang po siya. Yun po ang mangyayari. So, next step to that is that we have here the list of B of length n from step J minus 1 spans V, and thus adjoining any vector to it produces a linearly dependent list. So, kung linearly independent, so dapat equal lahat ng mga vector sa 0. Pero dito, lalabas yung dependent. It will contradict the properties of being linearly independent. In particular, the list of length n plus 1 obtained by adjoining uj to b, placing it just after u1 to uj minus 1 is linearly dependent. So by the linear dependence lemma again 2.4, one of the vector in this list is in the span of the previous ones. And because u1 and uj, because the set of u's or the vectors of u's is linearly independent, this vector must be one of the w's, not one of u's. So we can remove that w from b, that a new list of b length n consisting of only u's, and the remaining w's spans v. So yun po ang mangyari kasi papalitan natin ng papalitan. So after that, we will have again the step m. The step m, we added all the u's and the process stops. So pag in-add na po natin yon, doon na po ang last procedure natin. If at any step we added u and no more w's to remove, then we would have a contradiction. This must be at least as many w's as u's. So dapat kung gaano karami yung w's, ganun din kadami yung u's mo para mapalitan po lahat ng w's. Yun po yun. Para maging linearly dependent po siya. So 2.7 proposition. We have here a proposition. Every subspace of a finite dimensional vector space is finite dimensional. So again, we will prove this using the two steps again. So as proof, suppose B is a finite dimensional and U is a subspace of B. We need to prove that U is a finite dimensional. We do this through the following multi-step construction. Okay, step I. If U is equal to 0, then U is a finite dimensional. And we are done, of course. But if U is not equal to 0, then choose a non-zero vector which is an element of U. Okay. Now, step J, if that's the case, if U spans the vector, then U is a finite dimensional and we are done. If U is equal to the span of vector, then choose a vector Vj, which is an element of U, that Vj is not an element of the span of V's or vectors. After each step, as long as the process continues, we have constructed a list of vectors such that no vector in the list is in the span of the previous vectors. Okay, so thus, after each step, we have constructed a linearly independent list by the linear dependence lemma 2.4. So that would be the outcome of our procedure. This linearly independent list cannot be longer than any spanning list of V. That is by our 2.6. In our 2.6, which is we proved earlier, which also states that in a finite dimensional vector space, the length of every linear independent list vector is less than or equal to the length of every spanning list of vector vectors. And thus, the process must eventually terminate, which means U is a finite dimensional. Now we have here, next topic, we have what we call bases. So we'll define first bases. A basis of V or a basis of a vector is a list of vectors in V that is linearly independent and spans V. Okay. So dalawa ang quantifiers niya. First, linearly independent. Second, spans V. Example of that is, of course, we have this kind of example. And that is the basis of F raised to n. And that is called as the standard basis of F of n. And in addition to the standard basis of F raised to n, it has many other bases also. So with that, another example is that we have 1, 2, and 3, 5 is a basis of F2. The list 1, 2 is linearly independent but is not basis of F2 because that not span F2. So, ang 1, 2, and 3, 5 is a basis of F2. And it will also span F2 because dalawa sila. But the list of 1, 2 is linearly independent but it's not a basis of F2. Okay. Because linearly independent nga po siya pero hindi niya span ang F2. Yun po yung punto. So the list 1, 2, 3, 5, 4, 7 spans F2. But it's not a basis because it is not linearly independent. Yun naman ang pinagkaiba. As another example, 1Z to Zm is a basis of Pm of F. Okay. So, a list of vectors in V is a basis of V if and only if every V of element of V can be written uniquely in the form of V is equal to the sum of a linear combination A1, B1 to AN, Bn, where A, of course, is an element of F. To prove that, suppose that vectors is a basis of V. And let vector be an element of V. Because the vector spans V, there exists A's, which is an element of F, such that the 2.9 holds. So we'll show 2.9 earlier, which states that, okay, yung sa previous slide natin, 2.9 is V is equal to the sum of the linear combination. Okay. So, to show that the representation in 2.9 is unique, suppose that B1 and Bm are scalars so that we also have this second vector. Subtracting the last equation, we subtract A minus B, An, Bn. So this implies that each Aj, Bj is equal to 0 because B1, Bn is linearly independent. And hence, A1, B1 until Bn are all equal. So that's what it implies. So we have the desired uniqueness completing the proof in one direction. So the other direction also, suppose that every V is an element of V can be written uniquely in the form by 2.9. So clearly this implies that V1 and Vn spans V. So to show that the vector is linearly independent, suppose that A is an element of F such that 0 is equal to the sum of the linear combination. So the uniqueness of the representation of 2.9 with V is equal to 0 implies that A1 is equal and all A's are equal to 0. Thus, the vectors is linearly independent and hence is the basis of V. So we have also another one. We have here Theorem 2.10. Every spanning list in a vector space can be reduced to a basis of the vector space. So to prove that, suppose vector spans B. Okay. We want to remove some of the vectors from B so that from B's so that the remaining vectors form a basis of B. So we do this through multi-step process described below. So let's see. Yung ginagamit pa rin natin po yung step 1, step J, step M, kung mga steps po. So start with B is equal to this. So step 1, we will have if B1 is equal to 0, so delete B1 from B. If B1 is not equal to 0, leave B unchanged. Then, for step J, if Bj is a span of B's, delete Bj from B. If Bj is not in the span of B's, leave B unchanged. Okay. So stop the process after step N, getting a list of B. So this list B spans B because our original list spans B. And we have discarded only vectors that were already in the span of the previous vectors. So the process ensures that no vector in B is in the span of the previous ones. Thus, B is linearly independent by linear dependence lemma 2.4. Hence, B is the basis of V. Right. So, we'll have here a corollary. Every finite dimensional vector space has a basis. Of course, it is very clear, but let's show some proof. So by the definition, a finite dimensional vector space has a spanning list, as we proved it earlier also in the previous theorem. And also, the previous theorem tells us that any spanning list can be reduced to a basis. Another one, we have every linearly independent list of vectors in a finite dimensional vector space can be extended to a basis of the vector space. So to prove that, suppose V is a finite dimensional and V's is linearly independent in V. So we want to extend V's to a basis of V. So we do this through multi-step process as I describe it also below. So firstly, we let W's be any list of vector in V that spans V. Our step I will be if W1 is in the span of V's, let B equal to V's, letter V's. If W1 is not in the span of V's, let B is equal to V's and W1. Okay, that is our step I. In our step J, if double J is in the span of B, leave B unchanged. If WJ is not in the span of B, extend B by adjoining BJ to it. So after each step, B is still linearly independent because otherwise the linear dependence 2.4 would give a contradiction. Recall also that our B's is linearly independent and the Wj that is adjoined to B is not in the span of the previous vector in B. After n, the span of B includes the W's. Thus, B obtained after n spans V and hence is the basis of B. We have also here, suppose V is finite dimensional and U is a subspace of B. Then there's subspace of B such that B is equal to U to the direct sum of U and W. So proof. So to prove that, because B is a finite dimensional and so is U as presented in 2.7, thus there is a basis for use of U as shown in 2.11. So of course, U is linearly dependent list of vectors in B, and thus it can extended to a basis of list of U's and W's of V as presented in 2.12 that we need to adjoin them. Okay, so let W is equal to spans of W. To prove that W is equal to the direct sum of U and W, we need to show that V is U plus W and U intersection W is 0 to show that it is also unique. So to prove the first equation, suppose that B is an element of V. Then, because of the list of U's and W's spans B, there exists a scalar A and B, which is an element of F, such that, of course, the vector is comprised of U and W. In other words, we have B, which is U's, comprised of U's and W's, where U is an element of U and W is an element of W and are also defined here above. Thus, U, which is an element of U, which thus I mean V is equal to U plus W, completing the proof that V is equal to U plus W. To show also that it is unique, or independent, to show that U intersection W is equal to 0, suppose that B is an element of U intersection W. Then there exists a scalar of A and B, which is an element of F, such that the vector is comprised of a linear combination of V of AU and also equal to the sum of the linear combination of BW. Because U and W, thus the linear combination of AU minus to the difference of the linear combination of BW will then be equal to 0 if they are linearly independent and if the intersection is 0. Because the U and W's is linearly independent, this implies that A's from A to A sub M is equal to B until B sub N, which are all equal to 0. Thus, V is equal to 0, completing the proof that U intersects W is equal to 0. So that is for our topic on bases. We'll proceed now for the topic dimension. What is a dimension? So the dimension of a finite dimensional vector space is defined to be the length of any basis of vector space. The dimension of V is the finite dimensional is denoted to DIMV or DIMV, or denotes for dimension of V. As example, dimension of F raised to N, N, and dimension P sub M of F is equal to M plus 1. Okay. So it tells that also that any two bases of finite dimensional vector space have the same length. Again, any two bases of a finite dimensional vector space have the same length. To prove that, suppose B is a finite dimensional. Let B sub 1 and B sub 2 be any two bases of V. Then B sub 1 is linearly independent in V, and B sub 2 spans V. So the length of B sub 1 is at most the length of B sub 2, using our previous idea in 2.6. Interchanging the rule of B sub 1 and B sub 2, we also see the length of B2 is at most the length of B1, of course. Thus, the length of B1 is equal to the length of B2 as we desired to prove. Also, if V is a finite dimensional and U is a subspace of V, then the dimension of U is less than or equal to the dimension of V. So to prove that, suppose that V is a finite dimensional and U is a subspace of V. Any basis of U is linearly independent list of vectors in V, and thus can be extended to a basis of V, as our idea in 2.12. Hence, the length of the basis of U is less than or equal to the length of the basis of V. Another idea is that if V is a finite dimensional, then every spanning list of vector in V with length dimension of V is a basis of V. So to prove that, suppose dimension of V is equal to N and V's spans V. The list of V's can be reduced to a basis of V, as the idea showed in 2.10. However, every basis of V has length n. So in this case, the reduction must be trivial. 1 meaning that no elements are deleted from V's. In other words, V's is a basis of V, as we desired to prove. Okay. Additional idea is that if V is finite dimensional, then every linearly independent list of vector in V with length of dimension of V is a basis of V. So to prove that, suppose dimension of V is equal to n, and V is linearly independent in V. The list of V's can be extended to a basis of V, as the idea in 2.12. However, every basis of V length n, so in the case the extension must be trivial, meaning that elements are adjoined. Again, no elements are adjoined to V's. In other words, V's is a basis already of V, as we desired to prove. And lastly, we have here a theorem. If U1 and U2 are subspace of a finite dimensional vector space, then the dimension of the sum of U1 and U2 is equal to dimension of U1 plus dimension of U2 minus dimension of U1 intersection dimension of U2. So proof. Let U's be a basis of U1 intersection U2. Thus, dimension of U1 and U2, dimension of the intersection of U1 and U2 is equal to M. Because the U's is basis of the intersection of U's, it is linearly independent in the U1 and hence can be extended to bases as U's and V's of U1 as the idea of 2.12 showed us earlier. Thus, dimension of U1 is equal to M plus J's, whereas M is comprised of U's and J's is comprised of V. Also, extend U's to be the basis of U's and W's of U2. Thus, dimension of U2 is equal to M plus K. So that is to partially prove that. As we continue to prove, we will show that U's, V's, and W is the basis of U1 plus U2. This will complete the proof because then we will have the dimension of U1 plus U2 is equal to M plus J plus K. And we know that M is present in all of it. Since M is present to all of it, then the dimension of U1 plus dimension of U2 minus the dimension of the intersection of U1 of U2. So it is clearly that the span of U's, V's, and W's contains U1 and U2 and hence contains U1 plus U2. So to show that this list is a basis of U1 plus U2, we need only to show that it is linearly independent. To prove this, suppose that the linear combination of A's and U's, the sum of the linear combination of A's and U's, B's and B's, C and W's is equal to 0, well, all A's, B's, and C's are scalar. We need to prove that all A's, B's, and C's equal to 0 so that the equation will be true. So the equation above can be rewritten. We can rewrite this into A negative, A sub 1, A U minus 1, or the differences of the linear combination of A and U's, B and B's, to show, which shows that the sum of CW's is an element of U sub 1. All the W's are in U2. So this implies that the sum of the linear combination of CW's is an element of the intersection of U1 and U2. Because the U's is a basis of the intersection of U1 and U2, we can write that the sum of the linear combination of C and CW's is equal to the sum of the linear combinations of du of du's for some choice of scalar d. But u's and w's is linearly independent. So the equation implies that all c's and d's equal to 0. Thus, our original equation involves a's, b's, and c's becomes the sums of the linear combination of AU's, BB's is equal to 0. This equation implies that all A's and B's are 0 because the list of U's and B's is linearly independent. So we know that all A's, B's, and C's equal 0 as we desired to prove. Above all, we have here, suppose V is a finite dimensional and use V is equal to the sum of U's, and dimension of V is equal to the dimension of U's. Then V is equal to the direct sums of U's. So to prove that, choose a basis for each UJ's. Put these bases together in one list, forming the list that spans V, as what it shows in 2.20, and has a length of dimension as shown in 2.21. Thus, this list is a basis of V by 2.16. And in particular, it is linearly independent. Now, suppose that U1 is an element of U1 and UM is an element of UM are such that 0 is equal to the sum of U's. We can write each UJ as a linear combination of the basis vector chosen of UJ. Substituting this linear combination into expression above, we have written 0 as a linear combination of the basis of V constructed above, as we construct earlier. Thus, all scalar used in linear combination must be 0. Thus, the use is equal to 0, which proves that V is equal to the direct sum of U's by the idea provided in 1.2.